All right, so we have covered three topics so far. We talked about how to fabricate devices. We talked about the governing mechanics at the simplest possible way. And then we talked about energy transduction at microscales, right? So what is happening is that we are basically getting to a stage that we now can design a MEMS, or at least be able to analyze it. And at this point, we have a micromechanical device. This micromechanical device needs to talk to the world. And the language is usually in electrical signals, right? So you, either in analog domain or digital domain, you have electrical signals that convey information for you. So the next topic we're going to cover is how to extract the data that you have generated in the mechanical domain mostly and convert it into a language or into a signal that a computer can understand or a human can recognize once you display it to them, right? And therefore this section, the fourth section of the course, is going to be about simple electronic circuits that can now take the data from the mechanical domain and produce an electrical signal proportional to them. This section has a new suggested reference. It's not mandatory. You can refer to this book if you need to, or if you want to check something in a bit more detail. I'll try to cover the material in a way that, with a little bit of reminders from your 251 course, you should be able to follow the material, and therefore hopefully you don't need to go and check a lot of different references. But if you want to check one, this is a good one, and it is available for use through the SFU library. You can have access to this online. You don't need to get the paper copy. So what we are going to cover over the next couple of lecture videos is, first, we talk about voltage producing sensors and how to interface with them, basically how to measure voltage. We talk about current producing sensors and ways of interfacing with them. We talk about the importance of differential measurements. This is essentially your go-to technique in the vast majority of the cases. So we briefly talk about why that is important and why we would prefer to do a differential, let's say, sensing or actuation in most cases. We'll talk about resistive sensors and methods to measure resistance. It's a combination of the current and voltage measurements, as you might imagine. And then capacitive devices. We saw that a good number of the MEMS devices that we're dealing with have a capacitive interface. So you need to be able to drive capacitive loads or read signals from the capacitive outputs. Then we talk about something that is a bit new to you. You, I'm sure, have used these devices or circuits before. These are oscillator circuits, and these are nonlinear circuit elements or circuits, not circuit elements, that produce a periodic signal for you, right? So we have used them a lot. Everybody that has a watch or any other system that is working digitally has a clock in their system. That clock is usually an oscillator. But there are tons of other applications for oscillator circuits. So we briefly show you how you can make oscillators. There are different types, but we keep it simple, and it's mostly about the types of the oscillators rather than the details. And then finally, we'll talk about noise and interference. This is again going to be a bit of new information for you. I don't think the topic of noise is properly covered in other courses, and it's definitely very, very important in mechatronics, right? So in communications, you have heard the term signal-to-noise ratio. In sensing applications, we'll talk about minimum detectable signals or resolution or things like that. But definitely a very, very important topic. We'll show you the sources of noise and then how to do noise calculations in the system that can have mechanical and electrical components. Once we learn about what noise is, we'll talk about a very important technique to do low noise measurements. So that's going to be a very simple case, but synchronous demodulation will let you have fairly low noise measurements even in a noisy environment. So quick reminders about what we want to use. I'm going to put the focus in this course, for this course, on op-amps. These are, and there are good reasons for that. All of you have taken 251, the electronic circuit course. You know that we can use transistors to do everything that an op-amp does, and maybe do it better. But for using transistors, you need to worry about keeping that nonlinear element happy. You want to bias it in the proper operating region. You have to worry about are you going to get the gain that you need, the coupling, AC-DC coupling between different stages, and all sorts of other issues. In most cases, we can do the same task with an op-amp without any sacrifice in performance if you're a bit careful. And in most situations, the circuit is going to be simpler. Most likely, it can have lower power consumption, and more importantly, it's going to be more reproducible and in terms of performance and what you get once you put it on the board. So here's an example why. If you want to make a transistor circuit, you need to have biasing, and you need to set the bias point at the desired location. You use resistors, for example, for biasing. The resistors have tolerances. Transistors have varying performance parameters, and at the end of the story, you get somewhere close to what you wanted if you do it right. But then the temperature variations come into play, and then the differences between devices and the differences between resistors and all those things. So you get a spread. You get a distribution for your, let's say, bias point values. But with op-amps, that's not the case. Usually, you buy an op-amp, and if you're not pushing that op-amp to its limits of performance, you get more or less the same behavior, whether you make it 1 or 2 or 10 of those circuits. Now, here's the good news. In many cases, even if you switch the op-amp to some other entirely newer, different, lower power, whatever, op-amp, again, as long as you're not pushing these op-amps to the limits of performance, the behavior is going to be very much the same. So life of a designer, a circuit designer, is easier with op-amps. And that's what we're going to stick to for this course. I mentioned transistors a couple of times, but we're going to stick to circuits that use op-amps for whatever the purpose of the circuit is. So what is an op-amp? An op-amp is or operational amplifier is a circuit with 2 inputs and 1 output. So in theory, ideally, the op-amp has just 3 terminals, where V out is some constant gain times the difference between the 2 inputs, right? So this is the expression for the output voltage of an op-amp. You look at the difference between the 2 inputs. Input 1 in this case is called inverting input with a negative sign on the op-amp. Input 2 is non-inverting with a plus sign on the op-amp body. And V out is the difference, so V2 minus V1 or V plus minus V minus times a constant gain. So that's the definition of an op-amp. Now, so that's what an op-amp is. An ideal op-amp has a set of additional properties. So the first thing is that the gain is infinite or very, very large. So infinite, almost, of course, is relative. In this case, infinite is somewhere about 10 to the 5, 10 to the 6 or so, right? So an op-amp has a very large differential gain. It also has a 0 common mode gain. And we'll talk about differential and common mode signals later on in this lecture. But common mode means when the 2 signals are equal. So if V plus is equal to V minus, V out is 0. Right? So there's really no amplification of common mode signals. They are common to both inputs. An op-amp has an infinite input impedance. Right? So both the negative and positive pins on that graph have infinite input impedances, meaning that if you connect any of those ports to any other circuit, that circuit will not notice it. They don't know that you're measuring or you're taking the voltage from that node. The op-amp has a 0 output impedance, meaning that the third terminal in that graph behaves more or less like an ideal voltage source. You can draw any current that you want from it without affecting the performance of the device. And then finally, an op-amp has infinite speed. What happens at the input immediately affects the output. So that's going to be an ideal op-amp, right? So we are going to see, or you have already noticed that, well, obviously by saying ideal, you mean that it doesn't exist. But typical op-amps that you can buy off the shelf are actually getting very, very close to these ideal limit or ideal characteristics, with the exception of infinite speed. A typical op-amp can actually be really, really close to the other ones. Infinite speed obviously is a bit of a challenge, but for some applications you can also have infinite speed. If you're amplifying the signal that comes from a thermocouple that is measuring the temperature in this room, well, those things change on the order of, let's say, at the fastest minutes. Any op-amp will have infinite speed in that application. But if you're talking about RF signals and things like that, then you're basically, you have to be concerned about the speed limitations of op-amps. Now, an op-amp cannot do all that magic on its own. When you have an amplifier, you have to have a source of energy that lets you take some of that energy and add it to your desired signal. And that source of energy in most situations is a DC supply. So an op-amp at the very least has one, but maybe two power supplies, DC power supplies. Sometimes you show them, sometimes you don't. So at the very least, a practical op-amp should give you 5 pins, right? So 3 for the inputs and outputs, and 2 for the power supplies. Sometimes you use ground as your negative supply, which is perfectly fine in single supply operations. In most situations, you have a positive and a negative supply if you can afford it, right? So, okay, so that's the definition. Now, let's see what are the implications of assuming that we have an ideal op-amp. So the first thing, and again, these things are reminders from what you had in 251. The first thing is that if V out is A naught times the difference between the two input voltages, well, assuming that you have a finite output voltage, which you normally do, right? So if you have, again, remember that we have 2 power supplies here. The output voltage of an op-amp cannot go beyond those 2 limits. You know, if you have plus and minus 5 volts, those are the limits for the output voltage. You cannot go beyond them. So V out is bounded, V out is limited. As long as that's the case, well, if A naught is very, very large, you can show that the difference between the 2 input voltages approaches 0, meaning that the 2 voltages track each other. So there is a requirement for this. Your op-amp has to have negative feedback around it. But, without directly shorting the 2 inputs to each other, the voltages on the 2 inputs will track each other. It's as if there's a virtual short, which you've seen in your previous courses. Why is it a virtual short? Because in a real short circuit, you can have current flowing between the 2 nodes. In a virtual short circuit, as we do here, as we have here, well, the voltages on these 2 nodes are the same, but there's no current going between them. This is true. This behavior or this assumption is true as long as you have the op-amp in its linear operating region. And we enforce that linearity through negative feedback, external negative feedback. Again, you've seen this before. We'll go through some examples, but that's a necessary requirement here. You have to have negative feedback from output to the input of your op-amp as you go through the loop and then come back, in order for the op-amp to behave linearly. Once it behaves linearly, you have that gain equation that applies, and then therefore the 2 voltages on the inverting and non-inverting inputs will follow each other. The other implication, or the other assumption of ideal op-amp was that the input resistance was infinite. Well, immediately you can conclude that the input current going into any of or either of these two inputs is going to be 0. Infinite input resistance means that there is no resistance here. It's like a short circuit. Therefore, no current goes into the terminals of the op-amp. These two rules are the golden rules of op-amp circuit analysis, right? There's a virtual short between the two inputs, and there is a 0 current going into the input. So this is a familiar example. An inverting amplifier. I have a voltage source here. I've enforced negative feedback through this R2. So I take the voltage at the output, convert it into current, and feed it back into the negative terminal at the input. Also, I take the input voltage and convert it into a current through R1. The way I do that is that the virtual short between the two inputs ensures that I have a virtual ground here, 0 voltage here. So therefore, the input voltage is converted into a current that I pass through R2 and get an output voltage. So the analysis, once you write it down, looks like this. And we've done this before, so I'm not going to spend too much time here. Now, the nice thing here is that I can get any gain I want by choosing the ratio of those two resistors. The gain is negative, which is usually not a big deal. The input resistance is R1. In this circuit, what VI sees as the input resistance of the amplifier is R1. And so this is great if you want to have a set amount of input resistance. Let's say if you want to have a set input resistance of 1 kilo ohm or 10 kilo ohms. Easy. You just put a 1 kilo ohm resistor there and you get what you want. If you want to have a very large input resistance, then we may need to use a different circuit. Practically, you want to choose R1 and R2s in the range of, let's say, about 100 ohms to maybe 100 kilo ohms. That's a reasonable range for these resistors. And that gives you a very wide range of values for the gain, achievable gain and input resistance. Here is an alternative or a modification to that circuit. Again, it's an old circuit that you probably remember from your earlier courses in electronics. But in this case, what I'm doing here is that I've made an analog adder. And actually, I'm going to leave this for you to solve. What happens is that the virtual short between the two inputs will create a 0 volt potential here at the inverting input. What that does is that it converts each one of the voltages here into a current. So I1 is V1 over R1, I2 is V2 over R2, and so on and so forth. You can add up all these currents at this node and pass them through RF. So once you do the calculations, the gain is going to be minus RF times 1 over R1 times V1, 1 over R2 times R2, V2, and so on and so forth. You're adding those input voltages with their own weights. You can have different values for R1s and R2s and so on and so forth. So that's an analog adder. There is a negative gain again issue, is not a big deal as we mentioned before. If that negative gain is really bothering you, you can use this circuit. It's a non-inverting amplifier. In this case, the feedback is again from the output to the inverting input, but I take a voltage sample in this case. And the output voltage is converted into a feedback signal through this resistive voltage divider here. And that's your negative feedback. If you go through the calculations with the assumptions of ideal op-amp, you can show that the gain is 1 plus R2 over R1. So we like this circuit because, first of all, the input resistance is infinite, right? So the input source is seeing the input terminal of an op-amp, and that terminal doesn't take any current, therefore it is an infinite input resistance that you get. The gain can be set by a ratio of resistors. That's great. And one of the applications of this non-inverting amplifier is as a voltage buffer, where I don't want a gain. I just want to take that voltage from a specific node in the circuit and mirror it somewhere else. Maybe I want to drive a load based on that voltage or do something that affects the main circuit. I can put a buffer in there. And to do that, I need a gain of 1, so I either set R1 to infinity or R2 to 0 or both. I usually do both. I just have a short circuit from output to the inverting input and that's it. But this is a circuit with infinite input resistance and any gain larger than 1 for U. So with that in mind, I'm going to go and talk about different types of sensors and the way they produce signals. The first category that we want to talk about is voltage generating sensors. So a lot of the sensors that we talked about, you already know some, produce a voltage at their output terminals in response to whatever that you're measuring. An example is a thermocouple, right? So a thermocouple had a hot junction and a cold junction, and then at the location of the cold junction you had a voltage difference between the two ends of the thermocouple that was proportional to the temperature difference between the two ends. We noticed that that voltage was usually very small, right? So you're talking about microvolts or so. And that is in most cases too small to be used, let's say by a microcomputer or for a display system or whatever. And you need to measure that voltage. And, well, that measurement is usually done by a first stage amplifier. At the very least, you want to have a buffer. You don't want to affect the source. This is a typical model for a voltage generating sensor. You have a source. That source has some output resistance. You want to measure this V source, but what you measure is the voltage after the output resistance, right? So you would like this voltage V measured to be as close as possible to V source. You want to eliminate the effect of R source in your measurement. So ideally, if you keep this end open, you will do that. That's the job, right? So if you keep this end open, R source will have no current through it, and therefore V measured will be equal to V source. But, you know, life is not that easy. So we'll talk about a couple of situations where you know, things get a bit complicated. Examples of voltage producing sensors include, you know, as we've mentioned, thermocouples, but there are also photovoltaic cells. These are sensors that produce a voltage in response to changes in light intensity. Piezoelectric transducers, if you go back and remember, you produce a charge across a capacitor, meaning that you produce a voltage. And if you measure that voltage, you can estimate the stress applied to the piezoelectric piece. So there again, a voltage producing signal. Pyroelectric sensors are sensors that produce a charge in response to heat, similar to piezoelectric devices, but in this case, the input is the heat, not stress. But then again, the output is capacitive. You have a charge across a capacitor, therefore a voltage. So in most cases, as we said, we want to eliminate the effect of this R source in your measurements. If you're lucky, you will have a sensor with a low output impedance, meaning that because of the physics of the device, this R source is already small. So some examples include inductive sensors, right? So inductive sensors where you have, let's say, a moving core inside a coil that you're using to do a displacement measurement. Inductors have very low impedances. You know, it's basically a piece of wire that you've wounded many times at small frequencies, at low frequencies especially. So you can actually do your voltage measurement without worrying too much about R source. Photovoltaic sensors that we just talked about in the above are another examples. You know, if you do it well, you use these as energy generators, right? You use them to convert the incoming light into electricity. And if you're doing that, your generator has to have low internal losses, right? So photovoltaic cells, if you do them right, if you make them right, will have low output resistances. So then again, you don't have to worry too much about R source. Some resistive devices will have low output resistances. Examples include metallic strain gauges. These do not produce a voltage on their own, so this is a bit of a, let's say, footnote here. They do not produce a voltage on their own. You need to pass a current through them in order to get a voltage from them. But as an example of a sensor with low output resistance, you can think about those devices. And then there are electrochemical sensors that you use to measure different parameters. It could be chemical concentrations, but you can also use them to make tilt sensors, for example, and then you can look up tilt electromechanical sensors. And again, you can think about these as a battery. And a good battery, has a very low output resistance. It's a good voltage source, right? And therefore, again, you may not need to worry about the output resistance of some of these electrochemical sensors. However, some of these sensors, or actually a good number of them, have a high output impedance. So when you attach your measurement unit to these sensors and you want to figure out what the produced voltage was, now you're measuring a ratio, a fraction of that voltage. You know, going back to your electric circuit theory, we measured here is now R in over R in plus R source times V source. It's not V source anymore. So in a circuit, we call a node to be a high impedance node if, let's say if you put some charge there, or if you have some current coming into this node, there are no low impedance nodes for that charge to dissipate, to go away, right? So basically the charge is going to hang around there for a long, long time, okay? Now, high and low are, as in most other situations, they depend on the context. In RF circuits, 100 ohms is high. In sensing applications, you may go up to gig ohms in order for something to be considered high. But nonetheless, a high impedance node is, or sensors with high output impedances usually give you a terminal that you can consider it to be a high impedance node. Examples of high impedance sensors include capacitive devices, right? So these devices, again, in most situations, if you have a charge on a capacitor and you want to measure it, the impedance is quite high because these measurements are usually done at low frequencies, and at low frequencies, the impedance of your capacitor is quite high. Hall effect sensors is another example. Again, you have these two electrodes on the two sides of your piece of, let's say, whatever conductor that you're using for a Hall effect. You don't want to draw any current between these two electrodes. So again, that's another example of a high impedance device. And a lot of resistive devices also have high impedances, including, for example, metal oxide, gas sensors, or a lot of other sensors. The piezoresistive sensors made of semiconductors can have high output impedances. So the goal here is to measure this V source as well as we can. We want to be as accurate as we can in terms of the voltage that we report here. The challenge is, right, if you knew our source, that would be just fine. With whatever R in, you would measure V measured, and you would know what V source is. The challenge is you usually don't know R source. R source, in many cases, is not that well defined. And therefore, the variability or the uncertainty in R source will affect the accuracy of your output. You can say that, we measured is this much plus and minus this much uncertainty because I don't know R source. It could be anywhere from, let's say, 1 kilo ohm to 2 kilo ohms. And with an R in of, let's say, 1 kilo ohm, that's a 30-40% variation in the output for the same input voltage. So how do we measure these voltages? And well, if you stick to this model for the sensor, and remember this is the Thevenin equivalent circuit, right? So the sensor doesn't have to be that simple, that just a source and a resistor. It could be a fairly complicated circuit, but we can reduce it to a voltage source and a series resistance as long as everything in there is linear. So what we want to do is we want to measure that V source in this simplified diagram We want to minimally load the source. In most situations, your source may not be able to drive a low impedance voltage measurement unit, and it cannot provide the current. If you have a charge on a capacitor and you want to measure that voltage in order to estimate the charge, if the input resistance of your capacitor, your voltmeter is small, you're going to deplete the charge through the charge on the capacitor through the input resistance of your measurement system. So we want to minimally load the source as much as possible. On the other hand, we also want to make sure that the source is doing whatever that it is supposed to be doing, right? It should not know that we are taking a measurement. It should just behave as it was. And also, another advantage of having a very large input resistance is that you become insensitive to variations in R source. So let's say if your R source can vary between 10 kilo ohms and 100 kilo ohms. That's a very wide range. Usually you shouldn't have such a huge range for input resistance for R source. But let's say it does, a factor of 10 to 1. If I use R in that is 1 mega ohms, then that ratio we measured at worst is going to be 0.9, at best it's going to be 0.99. I'm going to have a 10% error in when we measured when R source changes by a factor of 10. If you make R in to be 10 mega ohms, your error in V measured will be only 1%. If you make R in 1 giga ohms, changes in R source don't really matter practically anymore. So that's another reason that I would like to have a very high input impedance. And then I have control over this area, right? This is my voltage measurement circuit or unit. I have control over that. So I put a lot of effort into making sure that R in is as large as possible for that particular application, of course, right? For typical voltmeters, that input resistance is somewhere between 1 mega ohm and 1 giga ohm. That's typical. So this is your benchtop voltmeter, can have an input resistance of 100 mega ohms to 1 giga ohms. The handheld voltmeter has an input resistance of 1 to 10 mega ohms. If you need more input resistance, that's possible. There are devices that are called electrometers. They essentially have an open circuit at the input. And what you measure is the field, the electric field that is produced by the voltage you apply to the input of these devices. So you convert the voltage into a field and then measure the field. And the input resistance can be more than a tera ohm in that kind of situations. Because I want a high input impedance, I need to use an amplifier stage that has a high input resistance. If you're making transistor stages, you use common source or common emitter stages or common drain or common collector stages. If you're not using a transistor amplifier, you want to stick to some, let's say, simplified version, you use a non-inverting op-amp stage. So if you choose the right op-amp, your input resistance easily can be on the order of hundreds of mega ohms or higher. At the end of the story, measurements from high impedance sources is not easy. The issue that, as we just mentioned, one in the above, is that the source may not be able to handle the extra load that you need from it because of the input resistance of your device, right? So you have, the example was the piezoelectric device or a charge capacitor. As soon as you have some small input resistance, the charge goes away. So the source may not be able to drive the measurement system. Frequency response in most situations is affected by the measurement. As soon as you contact that point, you have an additional R. We are normally ignoring the speed issues in a lot of our measurements, or we haven't talked about them in too much detail so far. But you always know that there's always something that limits the speed. It's in electric circuits, you usually model them with RC combinations. So as soon as you have additional R in your circuit, you're affecting the RC, the capacitance resistance time constants. There could be additional thermal noise once you add this additional R into your circuit. And that could, again, affect the measurement resolution in some situations. We'll talk about that later. And if you have a high impedance node, that high impedance node is more susceptible to interference. It's easier, basically, if there is a signal from in the environment, it could be the 60 hertz or it could be anything else in the environment. If this node has a very high impedance, meaning that if this is a high impedance node, meaning that once you put a charge here, it takes a long time for that charge to go away. If the impedance to everywhere else around this node is high, well, an interfering source here will be capacitively coupled to here. You may have a relatively low impedance connection between this signal source here and this high impedance node in your circuit. So once the impedance between this node and everywhere else is huge, is large, now you have to worry about the impedance between this node and all these other random sources in the environment. Okay, so coming back, when you have a high impedance sensor, be careful. A large input resistance is your friend when you're doing voltage measurements, but be careful. Again, a large input resistance can do some damage to your system as well, or to your measurements as well. Now, we talked about voltage producing sensors. There are devices or sensors that produce currents. In this case, we can represent them as their Norton equivalent circuit. It's a current source in parallel with a output resistance of that current source. There are tons of examples of devices that produce current in response to your input. One is a photodiode. I usually measure the reverse current through a diode, and once you have a different level of light, the current changes if the junction is exposed. It behaves more or less like a current source. You can see that there's no change in current with voltage, but the current is changing with light intensity. Some electrochemical sensors behave as current sources. We talk about some that act as batteries. There are some that act as current sources. And then there are ion-based sensors that, for example, are used to measure radiation. Or there are types of pressure sensors out there that actually measure a flow of charged particles, electrons, for example. So there are those devices that, again, once you have a certain number of ions going through this, let's say, barrier at a certain rate, you have a current, right? So current measurement in general is a little bit trickier than measuring a voltage. For a voltage measurement, you in most cases have a reference node in your circuit, so you have a ground connection, let's say we call it ground, and you just probe whatever voltage that you want to measure at any node in your circuit. As long as your probe has a very high input impedance, you should be okay. You should be able to measure those voltages at least at low frequencies with no problem. Measurement of the current, however, requires you to insert your current sensor into the branch where you want to measure the current. And that's intrusive. You have to cut the track open, put your sensor in there so that the current that was flowing in that branch goes into your sensor or your current measurement system and comes back and goes through its business. It's an intrusive measurement compared to voltage measurement. And because now you're inserting a new element into your circuit, the challenge is your circuit behavior may change. And that's one problem. And your measurement system, whatever you have here, can start to inject noise into your sensor circuit. That's also a problem. The other thing is that you need a floating current measurement system. So something that you can actually go and insert into a circuit, contact one end, contact the other end, so that the current goes through and comes back. So this measurement system itself has to be floating. You have to have a system that can be inserted into the circuits. And what is this measurement system? In most situations, it's a resistor. Right? So what you do is that you insert a resistor into that branch, into wherever that you want to measure the current. And the current goes through your resistor. You measure the voltage drop across that resistor and convert it into a current. Already you should be able to see some problems there. Right? So once you insert the current, especially if it is a low impedance node or low impedance branch, inserting a resistor there can become challenging. So here's one example. Let's say you have a high voltage power line where kiloamps of current flow through that line. If you insert a 1 milliohm resistor in that line, you are going to produce many, many volts across that resistor, right? But getting a 1 milliohm resistor is not that easy. We talk about contact resistance and things like that very soon. So you're going to get a 1 ohm resistance instead. But the 1 ohm and 1 kiloamp, you're producing so much voltage. And then also you're putting so much power through that device. Now, if that is not possible, if there's no way for you to insert a resistor into a circuit and do the measurement, there is an indirect way of measuring the current. What you do in this case is that whenever you have current flow, you produce a magnetic field around that piece of conductor. You can measure that field and estimate the current. So the relationship between the field and the current is as shown here. I is the current through the conductor, and R is the distance from the center of the conductor. Right? So it is proportional to 1 over R. And right away you see that, okay, great. It looks like it's a touchless way of measuring the current, and you definitely use this, but here is the challenge. This mu here is on the order of 10 to the minus 7. Right? So let's say if you have a 1 amp current, let's say 10 milliamp current, and you're measuring that field at a 1 centimeter distance, so the 10 milliamp and 1 centimeter cancel each other here, your magnetic field that is produced is on the order of 10 to the minus 7 Teslas. And that's a tiny field. And measuring that tiny field is not easy. There are not that many sensors that can measure such a weak field. And therefore, if you're dealing with small currents, this measurement method doesn't really work very well. Nonetheless, there are sensors out there, especially in power applications when you're talking about amps and kiloamps, where a sensor like this can actually be just fine. For voltage measurement, we said the typical input impedance for my systems or my voltage measurement systems is on the order of a megohm to a gigohm. For typical current measurement systems, the resistances have to be small. You're talking about milliohms to 100 ohms. And therefore, if you set this input resistance as small as possible, hopefully, for the same or similar reasons that we talked about voltage measurement systems, you can get rid of the effect of R source on your measurement. Here, most of the current will flow through Rn, and R source should not affect that value that much. And this is a note that we already talked about, that when you're doing a current measurement, because you're inserting a test instrument into your, or test component into your circuit path, signal path, you may be injecting noise and interference in there. So it has to be done carefully. Now, how do we measure this current? With the voltage measurement circuit, it was easy. That's something we've seen so far in our, let's say, electronic courses, that let's say a non-inverting input stage has a very high input impedance, and I can use that to measure the voltage. How do we measure currents? What are the amplifier stages that we can use to measure currents? So here is a simple one. Other than the one that we just mentioned, that you insert a resistor there and you measure the voltage drop across it, sometimes you just want to measure the current, right? You don't want to convert it into a voltage first. You want to get the current, amplify it, and then read out the value. A trans impedance amplifier can do that for you. So it's called the transimpedance because the output signal here is a voltage, the input signal is a current. So when you look at the gain of this, it's voltage over current, or same unit as impedance, but it's two different nodes in your circuit. So it is a transimpedance amplifier. What happens here is that the signal source, the current source, is connected to the inverting input of an op-amp. You have negative feedback on the op-amp, so therefore the voltage here is a virtual ground. And all of this current will go through RF. You can show that the voltage at the output is RF times I in. If the current is going downwards, you get a negative sign at the output. But voltage at the output is RF times the input resistance. Very easy to to convert a current into a voltage with, again, a footnote. Notice in here that the current that comes from your sensor goes through the amplifier and shows up at the output of the amplifier. You do not get the current back. You cannot loop that current back into somewhere else. So your sensor is producing a current, the current comes into your amplifier and you consume all of it. None of it goes back to wherever your circuit was. So this is the only footnote that you should keep in mind. If the current has to be looping somewhere else for whatever reason, you cannot use a transimpedance amplifier. Another side note is that your amplifier has to be stable with a loop gain of 1. Actually, a lot of op-amps are not stable with a gain of 1. So if you're picking an op-amp for this kind of application, make sure that to check the minimum stable loop gain, closed loop gain. You want to make sure that it is 1. If it is not stable with a gain of 1, you can still use it as a transimpedance amplifier, but you most likely have to add compensation capacitors here and there. The design becomes a little bit more challenging. For most typical situations, for most applications that you are dealing with, that is not worth the effort. Just go and pick a better op-amp or a different op-amp. Okay, so we talked about voltage and current measurement. Now let's talk about resistive devices. Well, we have seen this before. A resistance, the resistivity or conductivity of many materials is changing in response to something in the environment. Piezoresistors was one example where your device resistance would change with an applied stress or strain. Resistance itself is given by this expression for a long resistor with a uniform cross-section. Rho is the property of the material, the resistivity of the material. L is the length, and A is the cross-section for that resistor. If any of those three changes, you will have a change in resistance. In most situations, we are actually interested in changes in rho. It could be a light, it could be chemical concentration, or strain or stress, or things like that. So some examples are shown here. Now, because measurement of resistors is easy, people have actually used, let's say, potentiometers as part of their sensing systems. Right? So you basically, let's say, attach a potentiometer to a rotating shaft, and you can measure the angular displacement by measuring that resistance. So it's not a, property, it's not rho, L, or A that changes. It's a physical change in your resistor geometry. For example, you're adding length to it or you're subtracting length from it by rotating a knob. But at the end of the story, for your interface circuit, it's a resistive measurement. So the resistive interfaces are useful in that area as well. And we talked about changing resistor geometry. So how do we measure a resistance? This is the typical approach. What you do is that in here, in the shaded area, is your measurement system. Your measurement system produces a current. You send the current through your resistor. Once you have current going through the resistors, you will produce a voltage drop across this, and your instrument measures that voltage drop at the same time. again, you have a voltage measurement system, and therefore, for all those reasons that we talked about, we want R in to be much, much larger than R test. The current source may have its own output resistance that we hope is much, much larger than R in and R test as well. That may not be a very difficult task. If there is some output resistance for your current source, sometimes you can actually combine it with the input resistance of your voltage measurement system. And that R in includes the input resistance of your voltmeter as well as the output resistance of your current source. So we want R in to be much larger than R test so that when we pass a current through this, we measure the voltage drop accurately. So we therefore need access to both terminals of that device, right? It has to be a floating resistor. It cannot have one node connected permanently to somewhere else or both nodes. For example, it cannot be in a live circuit. It has to be accessible to us as a single resistor. Measurement of large resistors becomes tricky because, if you have a large resistor and you're sending a current through it and you want to measure a voltage, now R in may be comparable to R test. You start to get error sources in your measurements. And so that's on the high side. On the low side, if your resistance is less than 10 ohms, you have a different problem. Now, when you're doing that measurement and you have your current from the measurement system going into your R test, there's a contact here. There's a wire between the current source and the contact, and then after that to the test resistor, and then going back to the voltage measurement system. If your R test is small, all these add parasitic series resistors, right? So for example, the wire that you have here, let me go to the next slide. Between your I force, and R test, you have a PCB track. It has some resistance. The lid that goes from your measurement system to your resistor has some resistance. Once that probe touches a pad or another wire or whatever, there is a contact resistance between the two sides of that junction. So all of these appear in series with your R test, right? And then you have basically a similar set on this side. So when you send a current through this loop, you produce a voltage across the combination of all these resistors. What you measure is the voltage across all that combination. So if you just go and use a measurement system as we discussed before, you actually measure R test plus all of these. But you only want R test. All those other ones are parasitic. So how do we circumvent this problem? How do we address this challenge? The solution is using a 4-point probe measurement system. In this case, what I do is that I separate the tracks for forcing a current through the test resistors and measuring the voltage across it. Let's look at how I send the current. I send the current through a similar setup, right? So like what I had on the left side, I send the current through a similar setup. I have R track, R wire, all those contact resistances and everything else. I produce a voltage across this R test, and then the current goes back to the instrument over here. For the sense side, I use a different pair of probes. And these directly go to my voltage measurement unit. Again, I have R track, R wire, R contact, all those series resistors, I still have them. But because the input resistance of my voltage measurement unit is huge, there is not going to be any current flowing in this loop, right? So in this branch and in this branch, I will have almost zero current because the input resistance of Vsense is very large. And therefore, there is no voltage drop across these resistors because the current is zero. And therefore, what I measure is the true voltage across R test. If I know I force and I know the voltage across R test, I can estimate the value of R test accurately. So this is a very important measurement technique if you're measuring especially small resistances, right? Small, again, is relative, but we're talking about resistors on the order of ohms or tens of ohms. Okay, so what's next? Well, Wheatstone bridge is another circuit that you can use to measure variations in resistances. The challenge we have here is that, for example, if you look at this, let's say our test is a piezo resistor, and you're measuring that piezo resistor, and your hope is that you estimate the strain applied to that piezo resistor. That piezo resistor is very likely dependent on temperature as well. So if the temperature changes, the resistor value will also change. So at the end of the story, you will not really know if the change that you measured is due to a change in strain or stress or a change in temperature. So what do we do? Here is where a Wheatstone bridge comes to your help. Now, well, forget about the right side of this bridge for now. What I have is R1 and R2. I provide a voltage source, let's say DC voltage source, a fixed amount, and I measure the voltage at the top of R1. Let's say R1 is your test device. What I'm doing here is that by inserting that R2 into my circuit, I converted the resistance measurement into a voltage measurement problem. If I know the voltage at the top of R1, well, that voltage is R1 over R1 plus R2 times Vs. If R1 changes, that voltage changes, I can go and figure out what the change in R1 was, as long as I know R2, right? If I know R2, by measuring the voltage, I'm okay. So that's great, right? So I converted the resistance measurement problem into a voltage measurement problem. But here is another benefit. Let's say R1 and R2 respond similarly to the environmental changes. Let's say they respond similarly to your temperature variations. So in this case, if you're using R1 for measurement of a strain and R2 is your reference sensor, if R1 changes because of a temperature variation and R2 changes by the same amount, this voltage will not change. The voltage in the middle of them doesn't change. If R1 becomes R1 plus, let's say, 10, and R2 is R2 plus 10, the voltage doesn't change, the ratio doesn't change. But if R1 is subject to a strain and changes because of the strain, well, this voltage will now change because R2 does not see that strain and therefore stay the same. I measure a change here that is probably due to the change in resistance. That's all good and great with a minor problem. The problem is that let's say Vs is 10 volts and R1 and R2 are equal. I'm sitting at 5 volts normally. With zero signal, I'm sitting at 5 volts. Okay? With zero strain applied to R1, I'm sitting at 5 volts. Then 5 may go to 5.001 or 4.998 or whatever because of the changes in R1. But my voltage measurement system has to measure that 5 plus, let's say, 1 millivolt on top of it or 3 millivolts below it. But it has to measure that 5 initially. I need to have a lot of dynamic range at the input of my other system. To avoid that and get a zero signal for zero input, what I can do is that I can add the right branch, where I use, let's say, a similar combination of the resistors, and instead of measuring the voltage here with respect to ground, I measure the voltage here with respect to this side. Now, if all resistors are equal, let's assume at the beginning, V out will be 0 for when the resistors are equal. If V out is, and then if R1 changes, let's say R1 increases, this voltage goes up, this voltage stays the same as before, I measure a voltage difference between the two nodes. Let's say it's only 1 millivolt now, or it's only 3 millivolts. So I'm changing from 0 to 3 millivolts, or 0 to 5 millivolts. It's not from 5 to 5.001, it's from 0 to 0.001. And it's usually easier for your measurement systems to deal with that, for your voltage measurement systems to deal with that. You can have higher gain, you can measure smaller changes, all those things go with it. in that case, I have a complete bridge. It's called a Whitson bridge, and the advantage here is that it gets rid of the interferences that affect the sensors the same, and converts my resistance measurement into a voltage measurement problem. The voltage between the two nodes here is given by that expression. There are a few situations. At the end of the story, if you have similar resistors all around, they don't have to be the same, but if they are similar, this is the change in the output as a function of variations in the input. So the change in the output is half of delta R1 over R1 with that simplification, minus half of delta R2 over R2. Now, doesn't look like a good idea. If delta R1 and delta R2 are similar, I'm in trouble. I get zero output. However, in many situations, I can actually make delta R2 to be negative delta R1. Where, well, let's say if you're measuring the deflections of a cantilever, I can put a piezo resistor here at the top of this cantilever so that when the cantilever goes down, you stretch this and you measure an increase in resistance, for example. I can put a resistor at the bottom as well. And now I'm compressing that resistor, therefore the changes will be negative. So I have one delta R1 that is positive, one delta R1 that is negative. That can be done. So you can get delta R2 that is negative of delta R1, you get twice the sensitivity out of this bridge. You can also, we saw that when we talked about piezo resistors, that you have the longitudinal stress and the transverse stress on your piezo resistors. And the piezoresistive coefficients can be different, and actually in some cases one is positive, the other one is negative. So I can have a transverse piezoresistor here and a longitudinal one, and one of them will change, let's say, in the positive direction with an applied stress, the other one will be changing in the opposite direction. I can get a bridge that way as well. Okay, so that is my resistive measurement techniques. Again, I kept it simple. The next topic we want to cover is capacitive measurement, and this is very important. We have seen that, for at least the MEMS guys, in a lot of situations you produce a change in displacement, which is part of a capacitive interface, and you need to measure that change in capacitance to figure out what that change in displacement was. So a capacitance is given by this expression. Again, if I have two areas, A, in this case, two electrodes, A is their effective area, basically meaning the portion of the areas that they see of each other. So if it is like this, it's just this portion. If it is this, it's the entire electrode. G is the gap between them. I'm assuming parallel plates. And the capacitance is given by this expression. So epsilon R is the permittivity of the material between the two electrodes. In MEMS situations, it's mostly air or vacuum. Epsilon naught is the permittivity of vacuum, 8.8 times 10 to the minus 12 farads per meter. And A over G is the ratio of the area to the gap. We can make capacitive sensors where the G changes, right? The area changes, or the permittivity of the dielectric between them changes. So we just covered that. One reason that we like capacitive devices is that there is no DC current flowing through them, so the current consumption of the sensor itself is zero. Well, you obviously have to spend something on the interfacing side. The other reason that I like capacitive devices in most situations, especially if I don't have a dielectric between the electrodes, is that they're relatively insensitive to temperature variations. Temperature variations affect a lot of transduction mechanisms, not so much when we talk about the capacitive devices. However, and especially when you're trying to measure small capacitances, you have to worry about all these capacitive couplings between, let's say, in case of MEMS, you have two bond pads on the chip. The two wires are close to each other. You have a capacitance between the wires. If you're talking about PCB tracks, there is a track on the top layer, there is a track on the bottom layer. You can have capacitive coupling between the two. Or the two tracks that are nearby on one side of the PCB, you can have capacitive coupling between them. You can measure capacitance from measuring the impedance of your capacitive device. Typically requires you to produce an AC voltage. Basically, what you did for resistive voltage measurement, for resistive measurements, this time with an AC source. So instead of using a DC source to produce a current and then measure a DC voltage, now you do it in AC, high frequencies. If you know your device well enough and you can design your circuit to fit that device properly, this is doable. In most situations, this brings up some uncertainties, right? So the frequency response of the capacitor is important. The tracks that you use are important. You always measure R plus the CS. You know, you have some parasitic resistance in series with your capacitance. You measure that, and if your operating frequency is high, the importance of that parasitic resistance becomes larger and larger. You can do this, but in general, we don't, especially if it is a generic, capacitive measurement interface. You can measure charge, and if you know the voltage that produced the charge, you can estimate the capacitance. Remember, Q, the charge on the capacitor, is the capacitance times voltage, CV. That's actually the definition of capacitance. And oscillator frequency is a very common way of measuring capacitors. We'll talk about that later in this lecture. So how do we interface with capacitive devices? Let's assume that you have a biased capacitor biased with a voltage, right? A voltage source. We have charge sources, but they are not convenient. So when we talk about charging a capacitor, we mean that we use a voltage source to charge a capacitor. Once we have this charge on this capacitance, if you know the voltage and you measure the charge, you can estimate the capacitance. Or if you know the charge, and again, you measure the voltage, you can estimate the capacitance as well. Low frequencies, you want to measure that charge. High frequencies, it means that the charge is going back and forth. Well, instead of measuring the charge directly, you can measure a current that is produced by this charge going back and forth. So you can use, for example, your transimpedance amplifier in order to measure the charge through a capacitor at higher frequencies. Low frequencies, you're talking about kilohertz or less. You put a charge there, you measure the voltage. You have to do it fast enough so that the charge does not dissipate. You may use bridges, like the Wheatstone bridge that we just talked about, to measure capacitances as well. So you can put 4 capacitors in that band, around that bridge, and use an AC source and try to do the same thing that we did for a Wheatstone bridge. Again, as we said, measurement of impedances needs a little bit more care than measuring resistors. In many situations, we get a differential output from a capacitor. So why do we like differential outputs? So what does that mean? So it means that, let's say you have 2 sets of capacitors, and you've already seen this multiple times on the slides that I showed you in earlier portions of the course. Let's say you have a capacitor up here. So one electrode is going up and down, the other one is fixed. Once this electrode goes up, you have a capacitance that increases. If it goes farther, it decreases. I can measure that capacitor and figure out the gap. A better way of doing that is to put one electrode above this, one electrode below it. And usually we orient them such that the capacitance between this electrode and the top electrode is the same as the capacitance between the middle electrode and the bottom electrode. Now, if the moving electrode goes up, gets closer to the top electrode, the capacitance at the top increases, the capacitance at the bottom decreases. This is what we wanted. Remember, in Wheatstone bridge, that's what we wanted. We wanted one resistor to go up, the other one to go down. And in a Wheatstone bridge, you go and arrange them like that. So this goes up, this goes down, this goes up, this goes down, or vice versa. In a capacitive circuit, it's again an advantage. Instead of measuring an absolute C, instead of measuring C plus delta C, you want to just measure delta C. And what you do is that by having that differential configuration, you can subtract the two capacitors from each other, and you get 2 delta C at the output instead of C plus delta C. So here is the setup. You have the moving electrode here in between. This is the circuit equivalent, right? So in here, C1 goes up, C2 goes down, and you can actually look at the difference between these two. How do charge amplifiers work? So here is an example. Notice that the input current to your op-amp is 0. So what happens? Well, you can approach this in two ways. If you want to go the impedance way and go and say the gain of this amplifier is ZF, the impedance of the feedback loop, over the input impedance Z1, and with a negative sign, you can do that, and then you get this expression. However, the other way to think about it is that look at this situation here, right? So these two electrodes of CF and C test that are connected to each other, and no current goes into the input of the op-amp. Now, if you put a voltage here at the input, you put a charge. It's a certain amount of charge here. Let's say 1 picocoulombs of charge on this electrode. Well, you have to have the same amount of charge on the other electrode. You have to have 1 picocoulomb of charge here, but there is no way for that charge to come from the op-amp, so it just comes from CF. So you take 1 picocoulomb of charge from here, put it on C test. Well, now this capacitor is unbalanced. The op-amp will put the equivalent of 1 picocoulomb of charge on the right electrode of CF. And if you go and look at this charge distribution, you can show that at the end of the story, V out is minus C test over CF times V in. If you know V in and you know your CF, you can figure out what C test is and how much the changes in it are. Now, this looks simple, but again, nothing in the world is free and that easy. At the end of the story, you have to worry about the tiny, tiny charge that goes into the input of your op-amp. If your input bias current is 1 picoamp and you have 1 picocoulomb of charge, all it takes is 1 second for that charge to disappear completely. So maybe you want to go and pick an op-amp that has 1 femtoamp of input current. Well, at some point, you have parasitic resistances with these capacitors, or the PCB layout that you have. The tracks will have some parasitic resistances between them. You may lose the charge that way, right? So in these kinds of circuits, you need to worry about charge leakage and losing the charge because of the bias or other sources of parasitics. You can easily measure capacitors in the picofarad to nanofarad range with this circuit. And one thing you can do is to avoid or to reduce the effect of charge leakage or to circumvent that problem is that instead of using a DC voltage to charge C test, you use an AC voltage. A convenient AC voltage is a square wave in most situations. Square waves are easier to generate than sine waves. So you can use a square wave and go and measure the output amplitude and then figure out C test that way. If you have parasitic resistances, you may have some phase difference between the input and output. An alternative circuit, especially if you're using an AC signal at the input, is to just use RF instead of CF. This circuit gets rid of a lot of the problems that you have with the top circuit. However, the gain can be limited. If you increase the frequency here, your impedance here will be small. Over here, you can have a very large value of gain at the bottom. The low frequencies, you may not really get too much gain out of that circuit. Okay, so another category of amplifiers is switch capacitor charge amplifiers. And these are usually implemented using IC technologies, integrated circuit technologies. Very briefly, we're not going to get into too much detail here, but very briefly, what we do is that we have the same charge amplifier as before. But what we do is that we periodically discharge this capacitor, the feedback capacitor, and keep putting a known amount of charge on CS, discharge this capacitor before the measurements, put a known amount of charge here, and then send it to the output and low-pass filter to figure out the ratio of those two capacitors. This is done very easily at the integrated circuit level. Discrete levels, you have a lot of issues. Now, as we said before, if you are doing it that way, you're measuring C plus delta C. What I can do is that, I do not have any interest in the C part. I'm only interested in the delta C part. What I can do is that I can add a reference capacitance whose value is the same as your test capacitance and apply a negative signal to it, the opposite excitation to it. And by doing that, I cancel the C part. I only focus on the delta C part. Now, with this, I'm going to talk about differential measurement and differential sensing. So that's that for the capacitive sensing part and switch capacitors. But we talked about the challenge now that, I do not want to measure C plus delta C in most situations, or I do not want to measure V plus delta V or R plus delta R. What I want to measure is that delta R part, the delta V part, the delta C part. I don't care about R. There are other situations where I'm not interested in the absolute value of a quantity. So here is an example. Assume that you have made an amplifier. This is from your electronics textbook. You made an amplifier and you biased it properly to measure the signal from a microphone. This amplifier, the way you made it is that you went and applied whatever you learned in electronics to make your full wave rectifier and use that full wave rectifier to bias the circuit. Now, there are two signal paths. There is one signal that is your desired signal. This is the signal coming from the microphone that goes into your amplifier and then shows up here at the output. But if you remember, your full wave rectifier produces ripples here. It's variations in this voltage that you will get because of the way you produce the DC voltage there. And those signals, those ripples, can also come and show at the output through this RC. So if your VCC is changing like that because of the full wave rectification, and if your signal was supposed to be, let's say, something with zero, varying around zero, now your signal is varying around this superimposed variation. And you might have heard this in poorly designed audio amplifiers, that all of a sudden you start hearing the 60 hertz or 120 hertz. It's usually a low frequency signal that your ear picks up. The solution to that is to improve your power supply or figure out a way to do a differential measurement. Now, what I want to do is I want to go and produce a signal or look at a way to subtract this common interference from this signal so that I get my audio signal out only. So why do we want to have differential measurements or differential amplifiers? We want to look at the difference. This is one situation as described, that you have an interference on your signal and you want to get rid of the interference. You want to subtract the, let's say, main source from your signal. This increases your dynamic range. The next amplifier that comes afterwards, if you have, let's say, 10 volts plus and minus 1 millivolt here, and if you subtract the 10 volt from it, the amplifier has to deal with a 1 millivolt signal. Otherwise, it has to deal with the 10 volt plus 1 millivolt signal, which is much harder. If you go back and remember what you needed to do for your transistor amplifiers, for example. But another benefit of differential sensing is to discriminate against common mode interferences. So a differential amplifier goes and takes the difference between the two signals and multiplies them by a gain. Somewhat similar to what you saw for an op-amp, right? So an op-amp had a similar definition. The difference being is that in this case, AVD is not infinite. It could be a finite value. Now, a differential amplifier, so therefore, looks at the difference between the two inputs. Again, I'm sure you've seen examples of these before, right? So if you have an amplifier sitting to the far distance from your source, well, you can't take a pair of wires to connect, let's say, your microphone to your amplifier and take it across the room. But very few of you will do that. Why? Because, well, if you do that, you will have a huge interference coupled to your lines. If you have no other choice, what you do is that you go and create a twisted pair. So you try to go and twist the two wires to each other so that the interferences start to cancel each other along the length of the wire. But at the end of the story, you will have some interference coupled, even if you use a twisted pair. But it will be the same on both wires, as long as you keep things symmetric. If you use a differential amplifier at the end of this line, it just subtracts the two common interferences from both sides. So how do we deal with differential amplifiers or analyze differential amplifier situations? It's going to be easier if we come and make a definition here. So let's assume that we have this amplifier circuit. VI1 and VI2 are the two signals that go into it. Well, we always know that there are some power supplies, and Vout is at the output there. Actually, Vout should not be grounded, does not need to be grounded. So I'm going to fix that and post that the proper slides on the website. I define two new signals. One, VID is the difference between the two, right? VI2 minus VI1. And then the second signal is VICM, which is the average of the two, the common mode between the two, right? So 1/2 of VI1 plus VI2. So now if I do that, then I can take VI1 and say VI1 is actually equal to VICM plus VID. VI1 is VICM minus VID divided by 2. And VI2 is VICM plus half VID. And then, instead of having to deal with one source here, now I have three sources as shown here. But at the end of the story, I get my VI1 and VI2s back as shown there. You may wonder why I do that. Well, going from one source to three sources, what is wrong with me to make my circuit more complicated? Well, I do that because I want to use superposition next. So the superposition, when I apply it, I can keep VID only in my circuit and look at the difference. VID1 applied to one input minus VID2 applied to the second input. And that's one problem. The second problem is when I apply VICM at the same time to both inputs. For differential amplifiers, I keep everything symmetric in my design. From the input stage where I use and choose different transistors to build that circuit all the way to the end, I keep things as symmetric as possible. So by doing this, I can actually quickly show the response of the system or the circuit to the common mode signal, VICM, and the response of the system to the differential signal. If I have, let's say, 2 volts at one input and let's say 4 volts at the other input, the common mode signal is 3. The differential signal is plus half and minus half. So what I can do is that I can see how that symmetric circuit responds to this differential signal and to the common mode signal. And because of the symmetry of the circuit, breaking the two input sources into these two differential and common mode ones makes my circuit analysis more quickly. For you who are not getting too deep into this analysis of circuits discussion, the point to remember from this slide or this discussion is that V common mode is the average of the two inputs, and VI differential, or the differential signal when we talk about it, is the difference between them, the two inputs, any two inputs in the environment. And we apply half of it to one input and negative half of it to the other input. Usually, it's the inputs that are differential, but you can also have differential outputs. And again, we have a differential gain and a common mode gain. Ideally, I want the common mode gain to be as close to zero as possible, and A differential is what I want to have from my system. Once you have a circuit, the common mode rejection ratio, basically how insensitive your circuit is to common mode signals, is going to be given by this ratio. So these are numbers or values that you may see in, for example, an op-amp datasheet, that CMRR is 100 dB, meaning that the differential gain is 10 to the 5 times larger than the common mode gain. How do I make differential amplifiers? Well, this is one example with BJTs. I have my two input sources. If you want, I'll go through the solution for this during the live sessions, but I just want to know, you to know how we can make differential amplifiers. So in this case, I have two coupled transistors biased with a current source, and I have my inputs applied to the left and right of these, to the bases of these two. You can see that if this voltage goes up, well, I have an increase in VBE here. I take a larger portion of the current here. This voltage here will go down, and this voltage here will go up. Same thing here. If this goes up, then this voltage will go down, and this voltage will go up. The symmetry, remember that we mentioned everything is symmetric. If both of these voltages at the same time go up by the same amount, well, VBEs will not change. These voltages at these outputs will not change. So the common mode gain is zero. You have a differential gain, but zero common mode gain. If interested in analyzing this circuit, you want to see how it is done, you can go and check your Sedra and Smith or Razavi textbooks for the analysis. A MOSFET-based amplifier is the same. Very similar, you can go and have a look at how that circuit can be analyzed as well. But as I mentioned in this course, I don't want to focus too much on the transistor side. If you want to have a differential amplifier with op-amps, this is how you make it. So what I do here is that I combine three operational amplifiers inside a circuit. I call it the instrumentation amplifier, where the input stage here for, let's say, VS plus or VS prime here is a non-inverting op-amp. Same thing for the bottom one. Therefore, the input resistance that VS or VS prime are seeing is infinite in both inputs. I apply the signals to these two, and they produce a voltage proportional to VS and VS prime here. And I use a difference amplifier over here to subtract these two signals from each other. So V out at the end of the story you can show to be given by that expression over there. Now, this is different from an op-amp, right? So in an op-amp you had an infinite gain between the inverting and non-inverting inputs. In here you have a finite gain, right? So if you're making this circuit with op-amps, you can choose R3, R4, R2, and R1 to get your desired gain value. You can do that. There are, op-amp packages that have 4 op-amps in them. So you can easily make this with one package on your PCB. Or you may choose to buy an instrumentation amplifier. So these are devices that look like an op-amp from outside, same 8-pin package or things like that. But it's that circuit inside that package, the circuit on the left inside this package. What they do here is that they provide two terminals, in most cases, not always. Sometimes the gain is fixed. But they provide two terminals for you to set the gain. So in this case, the gain of this circuit is 1 plus RF over RG, for example, or 2 RF over RG, whatever, some combination. RF is an internal resistance. So they tell you that RF is, for example, 50 kilo ohms. and you go and choose RG to get the desired gain. So just by setting one resistor in there between the two terminals, you can get whatever gain that you want. And V out is just the difference between these two times the gain value. So these instrumentation amplifiers you can buy off the shelf and use them for your applications. Very easy to use, but as I said, at the end of the story, you get this circuit. So if you don't have an instrumentation amplifier, you can go and make one using 3 op amps as shown to the left. So that's that for the discussion on linear circuits, for measuring voltage, current, resistance, and capacitance. The next discussion or the next section is going to be about oscillator-based circuits, where we'll see how you can produce a periodic signal whose frequency or period is proportional to some value, some parameter of interest. So that's that for now, and I'll see you in the next lecture video. Thank you.